Ever wondered why medieval knights survived direct musket shots that would kill modern soldiers? Historical battlefield excavations reveal armor so advanced it could deflect early bullets while remaining surprisingly lightweight. These weren't just metal suits. They were engineered protection systems that outperformed modern body armor. Ready to discover the bulletproof secrets medieval armorers never revealed. Bullet deflection medieval armor was specifically designed with curved and angled surfaces that forced incoming projectiles to ricochet rather than penetrate directly. Battlefield archaeology shows bullet marks on surviving armor pieces, where musket balls literally bounced off the metal surface instead of punching through. The genius lay in understanding projectile physics centuries before modern ballistic science existed. Armorers shaped breastplates with pronounced ridges and curves that redirected kinetic energy away from the wearer's body. Museum examinations of battle-damaged armor reveal clear impact patterns where bullets struck at angles and deflected harmlessly away, proving medieval engineering superiority over brute-force projectile weapons. Steel composition medieval armorers developed unique steel alloys that combined flexibility with incredible hardness, creating metal that could absorb bullet impacts without shattering. They used specific carbon content ratios that modern metals still study today for their remarkable properties. The steel contained carefully controlled amounts of carbon, typically between 0.5% and 0.8%. which created the perfect balance between hardness and ductility. Furnace records from medieval workshops show that master armorers jealously guarded their steel recipes, passing them down through generations of craftsmen. Laboratory analysis of surviving armor pieces reveals steel compositions that rival modern ballistic materials in terms of impact resistance. Angled surfaces medieval armor featured sophisticated geometric designs that maximized deflection angles while minimizing vulnerable flat surfaces where projectiles could achieve direct hits. Every piece was carefully shaped to present sloping surfaces that would cause bullets to glance off rather than penetrate. The breastplate's distinctive barrel shape wasn't just aesthetic. It was pure engineering that created optimal deflection angles for projectiles coming from any direction. Helmet designs incorporated complex curves and ridges that could deflect projectiles upward and away from the face and neck areas. Master armorers calculated these angles through empirical testing, firing crossbow bolts and early firearms at test pieces. Layered protection knights wore multiple layers of protection that created a comprehensive defensive system, far superior to single-layer modern armor. The outer plate armor was just the final layer in a complex protection system that included padded undergarments, chainmail, and reinforcing plates. The innermost layer consisted of thick padded garments called gambesons, made from quilted fabric that absorbed impact energy. Over this went a chainmail hauberk that provided flexible protection against slashing attacks and projectiles that might penetrate gaps in the plate armor. This layered approach meant that even if a bullet penetrated the outer plate, it would lose energy passing through each successive layer. Weight distribution. Medieval armor used advanced weight distribution techniques that allowed knights to carry 60 to 80 pounds of protection while maintaining full mobility and combat effectiveness. The weight was carefully distributed across the entire body rather than concentrated in specific areas, preventing fatigue and maintaining balance during extended combat. Suspension systems, using leather straps and articulated joints, transferred weight to the strongest parts of the human skeleton, particularly the shoulders and hips. The armor was designed to move with the body's natural motion, using overlapping plates and flexible joints that maintained protection while allowing unrestricted movement during combat. Ballistic testing. Medieval armorers conducted extensive ballistic testing using crossbows, early firearms, and mechanical devices to ensure their armor could withstand real combat conditions. Workshop records from famous armor-making centers like Milan and Augsburg describe systematic testing procedures where finished armor pieces were shot with various weapons to verify their protective capabilities. They used standardized testing methods, firing projectiles at specific distances and angles to simulate battlefield conditions. Archaeological evidence shows proof marks on surviving armor, where armorers deliberately shot their finished products to demonstrate their quality to potential buyers. This testing revealed optimal plate thicknesses, curve angles, and steel compositions. Regional innovations. Different European regions developed unique armor innovations that enhanced bulletproof capabilities. while reflecting local combat conditions and available materials. Italian armorers perfected the smooth, rounded surfaces that became famous for their exceptional projectile deflection properties. German armor featured distinctive fluted designs that not only strengthened the metal, but also improved ballistic performance by creating multiple deflection angles. Spanish armor incorporated specialized reinforcing plates called placards that provided extra protection against firearms during their colonial campaigns. English armor focused on practical battlefield effectiveness, with designs optimized for longbow and crossbow protection that also worked against early firearms. Flemish armorers developed advanced articulation systems that maintained flexibility, while ensuring no gaps existed for projectiles to exploit. Each region's innovations were driven by the specific threats they faced, creating diverse bulletproof techniques that were shared through trade and warfare across medieval Europe. Production secrets: medieval armorers guarded revolutionary production techniques that created steel with bulletproof properties far beyond what the raw material suggested was possible. Master craftsmen used secret heat treatment cycles that involved precise temperature control and timing that modern metallurgists are still trying to fully understand. They employed specialized hammering techniques called penning that compressed the steel's grain structure while hardening the surface layers to incredible hardness levels. The forging process included multiple heating and cooling cycles that eliminated weak points and created uniform material properties throughout each armor piece. Workshop apprenticeships lasted 7 to 10 years because mastering these techniques required extensive hands-on experience. Quality control involved detailed inspection procedures where every piece was examined for flaws, tested for hardness, and verified for proper fit and articulation. Guild records show these production secrets were so valuable they were passed down only to trusted family members. Heat treatment: medieval armorers mastered sophisticated heat treatment processes that transformed ordinary steel into bulletproof material through precise temperature control and cooling techniques. They used specialized furnaces that could achieve and maintain exact temperatures for hours or days. The heating process involved bringing the steel to specific temperatures that varied depending on the desired hardness and flexibility. Characteristics for each armor piece: quenching techniques used various cooling media, including water, oil, and even air cooling to achieve different material properties in different sections of the same piece. Tempering processes followed quenching, where the steel was reheated to lower temperatures to reduce brittleness while maintaining hardness. Master armorers could create differential hardness across single pieces, making edges harder for impact. Resistance while keeping centers more flexible to prevent cracking. Impact absorption: medieval armor incorporated advanced impact absorption systems that dissipated bullet energy across large areas rather than allowing it to concentrate at impact points. The curved surfaces and internal padding worked together to spread impact forces over the entire torso rather than focusing destructive energy on small areas. Underneath the steel plates, specialized padding made from layers of felt cotton and leather absorbed and distributed impact energy while preventing the armor from transmitting force directly to the body. The armor's articulated design allowed individual plates to move independently during impact, further dispersing energy throughout the entire protection system. Internal suspension systems used flexible strapping slightly during impact, absorbing energy through controlled movement rather than rigid resistance. This absorption principle meant that even when bullets struck with tremendous force, the energy was converted into harmless movement and heat rather than penetrating damage. Laboratory testing of replica medieval armor shows impact absorption (RATES) that exceed many modern ballistic protection systems. The combination of steel composition, curved geometry, and internal padding created a comprehensive energy management system that could handle the massive kinetic energy of early firearms while protecting the wearer from both penetration and blunt force trauma. Joint reinforcement: medieval armor featured sophisticated joint reinforcement systems that protected the most vulnerable areas where plates connected while maintaining full range of motion during combat. These joints were typically the weakest points in any armor system, so armorers developed overlapping plate designs that eliminated gaps where projectiles could penetrate. The shoulder joints used complex systems of overlapping lames, small plates, that moved independently while maintaining complete coverage throughout the full range of arm motion. Elbow and knee joints featured articulated plates that flexed with natural body movement while ensuring no vulnerable spots were exposed during bending or extending. Hip and waist joints used overlapping skirt plates called folds that protected the lower torso while allowing for mounting horses and ground combat maneuvers. The neck joint between helmet and gorget was particularly critical, using overlapping plates that prevented projectiles from finding gaps while allowing head movement for vision and breathing. Master armorers tested joint reinforcement by having armored knights perform full combat movements while assistants probed for vulnerable spots with weapons. These reinforcement systems were so effective that properly made armor had virtually no weak points that projectiles could exploit, creating comprehensive protection that covered the entire body without sacrificing mobility or combat effectiveness. Surface hardening. Medieval armorers developed surface hardening techniques that created incredibly hard outer layers while maintaining flexible cores, giving their armor superior bulletproof characteristics. These processes involved controlled heating and cooling that affected only the outer surface layers of the steel, leaving the interior metal soft and shock-absorbing. Case hardening techniques introduced carbon into the surface layers through extended exposure to carbon-rich materials at high temperatures, creating steel surfaces harder than modern tool steel. The hardened surface layer was typically only a few millimeters thick, but provided exceptional resistance to projectile penetration, while the softer core prevented the armor from becoming brittle and cracking under impact. Differential hardening allowed armorers to vary surface hardness across different areas of the same piece, making some sections harder for maximum projectile resistance while keeping other areas more flexible for articulation. Surface texturing techniques created microscopic patterns that enhanced hardness while reducing the chance of projectiles finding smooth purchase points. Archaeological analysis shows that medieval surface hardening achieved hardness levels equivalent to modern high-carbon tool steels while maintaining overall flexibility. These techniques were so advanced that they influenced modern armor development and are still studied by contemporary metallurgists seeking to improve ballistic protection materials. Thickness variations. Medieval armor used strategic thickness variations that optimized protection levels while minimizing weight, creating bulletproof coverage where it was most needed without unnecessary bulk. Armorers made the front sections of breastplates significantly thicker than backplates because most projectile threats came from the front during combat. Areas used thinner steel to save weight and improve mobility. The thickness variations followed detailed anatomical knowledge, with armorers understanding which body areas could withstand more impact and which required maximum protection. Helmet thickness varied dramatically, with the faceplate and crown being much thicker than the back and sides, where projectile hits were less likely, and forearms while being lighter at protected areas like the upper arms and thighs. These variations were calculated through battlefield experience and testing, creating armor that provided maximum protection with minimum weight penalty. Modern analysis shows thickness variation patterns that demonstrate sophisticated understanding of ballistic threats and human anatomy. The strategic thickness distribution allowed knights to carry comprehensive protection while maintaining the mobility needed for effective combat performance. Battle performance. Historical battle records document numerous instances where medieval armor successfully protected knights from direct firearm hits that would have been fatal without protection. The Battle of Pavia in 1525 saw heavily armored knights surviving multiple musket hits while continuing to fight effectively against Spanish arquebusiers. Contemporary accounts describe bullets bouncing off armor like hail off a roof, demonstrating the effectiveness of medieval bulletproof technology against early firearms. Medical records from battlefield surgeons show that armored knights suffered primarily from blunt force trauma rather than penetrating wounds, proving that the armor successfully stopped projectiles while distributing impact energy. Veterans. Testimonies describe surviving direct cannonball strikes that dented armor without penetrating, allowing warriors to continue fighting after impacts that would have killed unprotected soldiers. The armor's performance was so superior that firearm development specifically focused on creating more powerful weapons capable of penetrating medieval protection. Battle damage analysis of surviving armor pieces shows impact patterns from multiple weapon types, with clear evidence of successful projectile deflection and absorption. These battlefield results validated the armorer's engineering and demonstrated that properly made medieval armor could provide protection levels that exceeded early modern military expectations. Historical context: medieval armor represented the pinnacle of pre-industrial engineering, combining centuries of metallurgical knowledge with sophisticated understanding of ballistics and human anatomy. These weren't crude metal suits, but precision-engineered protection systems that required years of specialized training to create properly. The development of bulletproof armor coincided with the rise of firearms, creating an arms race between offensive and defensive technologies that drove continuous innovation. Master armorers held positions equivalent to modern defense contractors, working closely with military leaders to develop protection against evolving weapon threats. The economic investment in quality armor was enormous, with a complete suit costing as much as a modern luxury car, reflecting the sophisticated engineering and skilled labor required for production. Archaeological evidence shows that medieval bulletproof techniques influenced armor development well into the industrial age, with some principles still used in modern ballistic protection. The decline of armor came not from inferior protection, but from changing military tactics that favored mobility and firepower over individual protection. Medieval armor represents humanity's first successful attempt at creating portable ballistic protection, establishing engineering principles that continue to influence modern military technology development. Subscribe for medieval military secrets. Hit bell for weekly armor wisdom that puts modern protection to shame.